Okay, so let us start off by recalling what we did in the previous video. We proved this result, that is, there is an isomorphism tau star star between these two quotient rings. This is one and this is the other. And keep in mind that our original setup has not changed. That is, there are two isomorphic fields f and f prime. Tau is an isomorphism from f onto f prime, and using tau we were able to set up an isomorphism tau star from the polynomial ring fx onto the polynomial ring f prime t. And then using tau star in turn we obtain this isomorphism between the quotient rings, and this isomorphism has these properties, which let us again also see the properties briefly. If you apply tau star star on alpha, then you get alpha prime, and keep in mind, recall that this alpha prime is actually nothing but the image of alpha under our original isomorphism tau. Okay, so tau star star behaves on the field elements like this, and it maps this particular coset x plus the ideal generated by fx onto this coset t plus the ideal generated by f prime t. And let us also, because we are seeing all the things, we are saying all the things, so let us also recall that f prime t is actually the image of fx under tau star. That's how we denote this. So this is nothing but fx tau star. Okay, so this is something we have at our disposal and we are going to use it. Now before we go to the actual proof of uniqueness of the splitting field of a polynomial, there is one more step that we need to take, and that step is this theorem. So let us first see what this theorem states, and then we are going to prove it today. So what the theorem states is that we are given a polynomial px over some field f, and px is irreducible. Okay, this polynomial px over f is irreducible, and it has a root v in some field extension of f. Then this field obtained by adjoining v to f is isomorphic to f prime w, where w is the root of this polynomial p prime of t. Here also our original setup has not changed. Still f prime is that field isomorphic to f, and our okay, so let's just see what p star t is. I mean p prime t is nothing but the image of p of x under that function tau star. Okay, so we have a root v of px and we have a root w of this p star t. Then there exists an isomorphism, a field isomorphism between these two fields. One is obtained by adjoining v to f, the other is obtained by adjoining w to f prime, and we are calling this isomorphism sigma, which has these two properties. The root v itself will be mapped onto the root w by sigma, and sigma behaves much like how tau star star behaves on the field elements, I mean the elements coming from the base field f. Okay, so let us now prove this. Proof. Let, well, the root is already given, but still the author, actually in the text the author starts off by assuming a root. Let's just write like how Herstein wrote. Let V be a root. So we will use this lemma at some point. We have already seen what it states, so now I am going to wrap the things up. Let V be a root of the irreducible polynomial Px in some extension K of F. Okay, we already know that there will be one extension which will have a root. We have already proved this particular result. Okay. Now what we are going to do, we are now going to consider a set of polynomials, namely that set of polynomials over F, all of which vanish at V. That is, let M be the set of those polynomials in the polynomial ring Fx which when you evaluate at V you get 0. Okay, so now the next observation is that this M is going to be an ideal of this polynomial ring. That's what we want to show. Show means the author has simply mentioned that this is an ideal, but we are going to still show this. Note that the 0 polynomial belongs to M. Why? Because if you evaluate 0 at V, it is going to be 0. The 0 polynomial evaluated at any point is actually 0. So in particular at V also it is 0. So that means M is a non-empty subset of Fx. For Fx and Gx, we should be careful to not use the polynomials that we already have here. That is Px, no? Okay. Okay, so for Fx and Gx belonging to M, we have, so both of them will vanish at V, that is, we will have this, hence okay, let me write like this, just to show that F minus G is the polynomial, which is of course their difference in the ring Fx, being evaluated at V. Okay, so that means Fx minus Gx or F minus G of x, or whatever you may want to call it, that now belongs to M. This implies this belongs to M. Actually, there is no need to separately show that M is an ideal, because right after showing this, we are going to set up a ring homomorphism of which M will be the kernel. So automatically it will be an ideal, but still it's a nice exercise to directly see that M is an ideal, although it's quite straightforward, but still. So this belongs to M. Also for any polynomial kx in fx, okay, so next I have to show that the product of say fx and kx again belongs to M. That is also easy. Fk, just like this one, I am writing Fk, which is just the usual product of fx and kx in the polynomial ring fx. Evaluated at v is, of course, f of v times k of v. This is equal to 0 times k of v, that is equal to 0. Thus, fx times kx belongs to M. Hence, M is an ideal of fx. Note one thing, that we are simply saying that fx kx belongs to M. That by itself is not enough to conclude that M is an ideal. It just tells you that M is a one-sided ideal, but the fact that our ring itself is a commutative ring makes it enough. Okay, and if you want to write a conclusion of this, I mean after this fx minus gx belonging to M, after this if you want to write a conclusion, it would be the thing that hence M is a subgroup of fx under addition. Okay, and this additional condition of course makes you conclude that M is an ideal of fx. Note that M is a proper ideal since the constant polynomial 1 is not in M. 1 being the unit element of the field F is also an element of fx, but 1 does not belong to M, because if you evaluate 1 at V, what do you get? You get 1 itself, because any constant you evaluate at anything in the field, you get that constant itself, and that is of course not equal to 0, because we are in a field. In a field, the multiplicative identity and additive identity, they have to be different. Now, we are going to, but before we define this, we need to say one more thing, that okay, so far we haven't done anything with px. Now we just simply took the root v of px, we set up one ideal M like this. Now we note the fact that px itself is an element in M. Since px belongs to M. Why is that so? Because p of v is 0 and that is because v is the root of p, that's why. Now since p of x belongs to M and p of x is irreducible, we have M equal to the principal ideal generated by p of x. The question is why. I leave this why to you. Okay. So what do you have to do? You have to show that any element in M, which of course is going to be any polynomial like this, is divisible by px. And in showing this, somehow irreducibility of px will play a role. Okay, so I leave this entirely to you. Irreducibility of px will make you conclude this, will give you this. Okay, so this I am just simply assuming like this, leaving the demonstration to you, and we move on. We now define we are now going to define a function, and that function is going to be this. Okay, I am a little confused. Is this fun? Oh, it will. Okay. No. This is not what we are going to define right now. This will come afterwards. First of all, we are going to define a function from the polynomial ring to this field by, shall I write it here? Let me continue from there. By this formula, you take any polynomial qx here in the domain, its psi image is defined to be the value q of p, which is that thing you obtain by evaluating the polynomial q at phi. Now recall that we have already encountered this type of function when we proved what was that theorem or lemma 512, which tells us that if you have a field f and an extension k of f and an element a in k, then A is algebraic over f if and only if this is a finite extension of f. In the proof of this result, we encountered this thing in that half of the proof, which is not the easier one, which is the more difficult one. and there we saw that this function, actually the exactly same function, not similar but the exact same function, there also we considered, here also we are considering. So there itself we proved, we saw that this function is a ring homomorphism, and that too a surjective ring homomorphism, that is onto. So we write, as we saw in the proof of, is it lemma or theorem? Psi is a homomorphism of fx onto fv. And because we are dealing with rings only and rings and fields, so no need to separately mention ring homomorphism. This onto fv with kernel. Okay, so what will the kernel be? Note that the kernel will consist of those polynomials which, when you evaluate at v, give you 0. That means the kernel is precisely our ideal M. With kernel precisely M. So you have, let me draw one diagram here because this will be necessary. This is something that we drew in the chapter on group theory when we proved the first isomorphism theorem. A similar thing is true here also. So here what I am doing, you see, we have an onto homomorphism psi whose kernel is M. Then by the fundamental homomorphism theorem, isomorphism theorem, whatever you may want to call it, there is an isomorphism between this quotient ring and this fv, and we actually know what this isomorphism is. What it does is this: you consider any element here, how does that element look? Fx plus M. So what you do, from this element you go to Fx, and then from Fx you go to its image under psi, that is Fv, and this sets up a mapping between which maps this coset onto this field element Fv, and that is the that turns out to be the isomorphism. If you go back to the isomorphism theorem in the chapter on groups, because there you have this diagram, there you will see that we have such a mapping which turns out to be an isomorphism between these two, and that to one that is onto. So these two are isomorphic. So in case of rings also the similar thing happens, and this we are going to call psi star. Okay, so next we write, this actually is for our understanding, it's not a part of the proof. I drew this here mainly for the properties of this psi star that we are going to next mention. Those properties will be clear from this diagram. Okay, so we have obtained this, hence by the fundamental homomorphism theorems or theorem, is it something specific or theorem for rings? Okay. Oh, so the author is calling this one the fundamental homomorphism theorem. It does not matter what we call it, the result is what matters. Ah man, this is again a very hot day. Anyway, so okay, so this there exists an isomorphism psi star from this quotient ring onto the field FV, extension of F actually, but a field ultimately, and which satisfies some properties. So these are the properties. Yeah, okay, so note further. So these properties have been written in another paragraph. Okay, fine. Whatever Herstein says. Note that alpha psi star is equal to alpha for all alpha belonging to F, and do we have anything else here? Oh, so that other thing involving that coset, so that is, he is again writing it separately. Summing up, how many times do you need to sum up things? Summing up, psi star is an, but that is what we have already written now. What is the point of repeating things? Psi star is an okay, what is the purpose of the isomorphism of, I don't know what's the purpose of writing this again, but let me just do whatever he has done. Maybe I'm missing something. Okay, so to be on the safe side, let me just again write. So an isomorphism of this onto FV that leaves all the elements of F fixed, which just simply means this. And that is why I need the diagram. Oh, and one more thing, we still need to justify how we are getting this alpha psi star equal to alpha, and that is why I have this diagram. Leaves all the elements of F fixed and I need some ink. And x plus m actually, but that m is precisely this principal ideal generated by Px. If we apply psi star on this, then we get V. Okay, so let us now see exactly how we are getting this and this. First of all, this. So what do we see here? What is the association? If we start from this coset, then its image under psi star is f of V. So when we are considering alpha, what is this coset? This is actually it is a coset. Keep in mind the identification, you recall there is an identification which identifies the field f inside this quotient ring. According to that identification, alpha is actually the same thing as alpha plus m, that is this. So you calculating alpha psi star actually means calculating this. So by our definition of this function, this is evaluating the constant polynomial alpha at V. So that gives us the constant itself, and that is why we are having alpha psi star equal to alpha. And what about this? Let us see this one also. So again, this is also a coset. So that means by the definition of psi star, this thing will be equal to the evaluation of the polynomial x at V, which is V itself, and that is why we have V. Okay, so now it's clear how we are getting these extra properties of psi star, and now we don't need the diagram. Okay. So we have got this psi star. Now whatever we did with fx, px, all these things, we are now going to do with the other things, f prime t, p prime t, those things. Since, in the next paragraph, since px is irreducible in fx, p prime t is irreducible in f prime t, and that is why and the justification for this is coming from lemma 533. Lemma 533 is that lemma which tells us that there is an isomorphism tau star between fx and f prime t, which is on 2. That means these two are isomorphic polynomial rings. So if you have px here which is irreducible, then its image under tau star, which is p prime t, also has to be irreducible in this polynomial ring. That's how we are getting this thing. So just like we set up this psi star, now we can set up another one, theta star, which behaves just like this. So we don't need to repeat all the arguments, we are just simply going to mention. So there exists an isomorphism theta star of f prime. I don't have space to write this. Theta star from f prime t quotiented by the principal ideal generated by p prime t onto f prime w. Note that just like v was any root of p of x, w is also any root of p prime of t, and we can use the w here just like we used v there. And this theta star also, just like psi star, has those properties. The diagram that I drew there a few moments ago, that type of diagrams become more and more frequent as we go to higher and higher parts of not just algebra but in many other areas of mathematics. And there is one particular subject where diagrams themselves are the main object of study, that is category theory. Onto this such that alpha theta star is equal to alpha for all alpha belonging to f and okay, let me just first try to write this on my own and then I will see if I am correct or not. P prime t theta star is equal to w. So mimicking what we did back then there with f and px and v, we have written the similar things for f prime t, p prime t and w. Okay, so is it really this thing? Yes. Oh, so there we wrote in words that theta star, psi star leaves the elements of c. I still made a mistake. It should be f prime. Here we have just same thing, no? Theta star leaves all the elements of f prime fixed. This part I think is okay. P plus p prime t, the ideal generated by p prime t. On that, if I apply theta star, then I get the root w of p prime t. Okay. So now we have all the ingredients, and we can now use them together. And so the language is very nice. We now stitch the pieces together. Okay. We now to prove our theorem, that is 533. And this is the point where we will use that lemma that we proved in the previous video. By lemma 534, there is an isomorphism tau double star of this onto f prime t quotiented by the principal ideal generated by p prime t. And has anything else been mentioned? Oh, which coincides, this particular function also has those properties, similar properties. This, however, does not exactly leave elements of f fixed, because here two fields are involved, not one field, f and f prime. So shall we write it like that, has the author written? No, he has written it in words, which coincides with tau. On f and which maps x plus the ideal this onto t plus the ideal this. If you write this in symbols, it will look like this. And maps this onto this is of course clear, but what is this? And how is this the same as this? Coincides with tau means what? Coincides with tau just means this, because alpha prime is alpha tau. It's just this alpha prime is nothing, it does not have any different meaning. It is just a symbol which is denoting alpha tau. Okay, so that is why since this becomes alpha prime, so the image of alpha under tau star star is the same as the image of alpha under tau. So that's why this tau star star coincides with tau on f. Okay, so now we will draw another diagram, and this diagram will help us set up the final isomorphism. So what we do, we stitch the pieces together. That means let us first see the objects that we have. We have fv and we have this quotient ring px. This way also some people write, okay, instead of writing using slash like this also some people write quotient structures. And then we have this other quotient ring p prime t, and then here we have this other field. Now we already have shown that there is an isomorphism psi star from this onto this, and this isomorphism between these two quotient rings is your tau double star. And just like this one, here also there is an isomorphism, and that thing is your theta star. Now because this psi star is an isomorphism, its inverse exists and is also an isomorphism, which will run from fv onto this, that is this. Now if you compose these functions, this, and this, then you get a function from f of v onto fv onto f prime w, and that function looks like this. It's the composition of these things, these three isomorphisms. And because each one is an isomorphism, so their composition is automatically also an isomorphism, and that gives you the isomorphism between fv and f prime w that we are seeking. And but that's not where everything ends. We still need to say those two properties are also true that we mentioned in the statement of the theorem. Okay, so this let the diagram stay here like this. Now we write, now we consider the composition. Category theory is a fascinating subject. It allows us to study the relationships between different types of structures. For example, relationships among groups and rings, or groups and topological spaces, relation between categories of groups, categories of vector spaces, categories of topological spaces, like that. So now we consider the composition, and this type of relations first of all arose in some parts of mathematics, and then later only people realized that there is something underlying which is deep, and it is saying many things about the things that were encountered sporadically in separate places. One such thing is Galois theory, towards which actually we are going, which somehow links groups with fields. Another such connection arises in algebraic topology, where you attach groups to topological spaces, and that association helps us study topological spaces much more efficiently, which is not possible by simple topological methods. Anyway, this composition sigma since these are all onto isomorphisms, sigma is also an isomorphism of f V onto F prime W. Okay, so now we need to show two things and then it will be over. One of them is that sigma maps V onto W, and the other thing is that sigma maps any element alpha in this field onto alpha prime, the image of alpha under our original function tau. So let us see the field thing first. Next, for any alpha belonging to F, we have, okay, so we are now going to apply, okay, this is going to be a little long, alpha sigma. So alpha sigma means alpha phi star inverse tau star star theta star. So what is it going to be? So we need to recall the things. What were the properties of psi star? Psi star is identity on the field F. Okay, you go back to the properties of psi star, you will see that psi star leaves the elements of F fixed. So its inverse will also leave the elements of F fixed. So that means this is going to be alpha tau star star, because this is alpha theta star. Now tau star star maps alpha onto alpha prime, and just like psi star is it does not change, it is identity on F, theta star is identity on F prime where this alpha prime is an element. So that means this is going to be alpha prime. That's how we get alpha sigma equal to alpha prime. Also, V sigma is V psi star inverse okay, do we have it here? We don't have it here, but this thing is equal to x plus px. The psi star image of this is V. So that means the inverse image of V under, the image of V under the inverse map is this. And we are considering T double star theta star of that. These things can quickly become very confusing. Okay, so it's better to have all the equations and all the relations in front of you, and then you start doing the calculation. If at any stage you get confused and you completely forget what you are doing, that is game over. And this thing is mapped by tau double star onto this, the corresponding thing in that other world, other quotient ring. And this thing, if we go back to the properties of theta that we wrote somewhere along the proof, is nothing but W. So that's how you get V sigma is equal to W. So sigma is an isomorphism with the required properties, and this completes the proof. We will use this proof, we will use this theorem finally in our final result, which we will not do today, where we will prove that essentially every polynomial has a unique splitting field. Now, before we end things though, let us mention one corollary to this theorem, which is also important. And the corollary goes like this: if Px belonging to Fx is irreducible and A and B are two roots of Px in some extension field that need not be mentioned. There is some field extension where Px has two roots A and B. Then the extension Fa and Fb are isomorphic. By an isomorphism that leaves all the elements of F fixed. By an isomorphism that actually maps A onto B. That also has been mentioned now. Yes. That maps A onto B and leaves all the elements of this fixed. It may not be immediately apparent how this corollary, how this result is a corollary to the previous one, or the same thing, how one actually will go about proving this corollary from the previous theorem. It's just simply this. In the previous theorem we had two fields, right? Now we have only one field. So you consider it twice, and the polynomial is also the same, Px. Okay, but the roots are different. Here we are considering the root A of Px, here we are considering the root B of Px. So Fa is isomorphic to F prime B. In this case, F prime is F itself. By an isomorphism that maps V onto W, that's sigma. In this case, V is A, W is B, and which leaves all the elements of F fixed, that we can say in this case, because actually we don't have two different fields, actually we have the same field. And in this case, if we are say calling this isomorphism sigma, this equation reduces to this equation. But exactly how? Keep in mind that this alpha prime originally was our image of alpha under tau, and tau is the isomorphism mapping F onto F prime. That was where all the things started. In this case, particular case where both the fields are the same, this tau is the identity map. So that is why alpha tau is equal to alpha. Okay, so that's how we get this corollary as a corollary to the previous theorem. So with this I end today. I mean, so tomorrow is Saturday, huh? So what did we do the previous Saturday? Did we solve? I think we solved Gallien's group theory exercises. So we now have to leave. We will do next week. Tomorrow let us do Gallien's ring theory exercises. I think we are going through integral domains right now. So we will solve a few. So with that I wrap things up. If you want to say something about these things, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. So that being said, this is it for tonight. See you tomorrow with Gallien's ring theory exercises. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.